Thank you very much. So I'm very happy to talk. This is the talk. So this is my talk about generalized quantum Stein lemma and second law of quantum resource theory. So first part, I will discuss our proof of the generalized quantum Stein lemma, and later I will discuss the second law of the quantum resource theory. This joint work with Hayashi and Yamasaki from University of Tokyo. So this content very simple. So firstly, I give our proof and statement and our proof, and secondly, I will discuss this one. So originally, Fernando's paper only discussed the state case, but in our result paper, we also extended that situation to the challenge. So this is a problem. So what is the general Stein lemma? So firstly, we need to consider a set of states, not one state. So in the case of this is a quantum relative entropy, and we need to consider a second argument of the relative entropy, but in that case, this second argument sometimes not one state. We need to consider a set of free states. This state should be convex and closed set. And also we have some tensor product structure. If we tensor product of the two and this one, so this free set include this one. So this is the big system, and this free state includes that small system, tensor product of small one. And also we need to assume that this set should be closed for the permutation about the order of the tensor product. This is also needed condition. And also this one contains some full rank state in the one copy system. So this is very easy condition. And then we need to consider relative entropy of this quantity. So we have an n copy state, and also we have a set of the free state, and we need to close minimum relative entropy between this one. So we need to minimize this quantity, and sorry, this is 1 over n, and we need to regularize. We need to consider regularization. So we need to divide by n and take n go to infinity. So this one has always, this one has a convergent point. Because due to this condition, we can show that lim super and lim inf should be equal. And finally, we need to do the problem of the hypothesis testing. So originally, Stein's lemma means that something with the hypothesis testing problem. So we consider the two candidates. One is a state of law, another one is sigma. But that sigma is not unique. So we need to consider worst case. This is the first kind of error. This error should be smaller than epsilon, and we need to minimize this one. But in that case, we consider worst case of this one, worst case of this quantity, and later we need to minimize this quantity under this condition. So this quantity is very important. Our interest is this one. So we consider n tensor product case, and we need to consider tensor product of free states. Of course, this one is a set of simple tensor product case. This is simple Stein lemma. So this is very easy. But now we need to consider some set of the free states. And this set of free states somehow growing up. This sometimes very big. Not only this tensor product one, and also this one includes some other state. Some other free state does not have this form. So we consider very large system, and we need to consider its limitation. So this one equal to this quantity. So this is general Stein's lemma. Of course, based on the Stein's lemma, we can show that this one is always smaller than this one. So or equal. So this one cannot exceed this quantity. This is not so difficult. This is comes from a conventional Stein's lemma. So, but nowadays we need to prove that opposite direction. So there exists some test to achieve this quantity. But in my proof, something like the contradiction, using a contradiction, we will not exactly construct the test to achieve this quantity. We only show that there is no, we assume that this strict inequality, then we have a contradiction. No, that proof is slightly complicated, but not so difficult, I think. So now we need to prove this one. Firstly, we need to consider this problem. So this one and this one is slightly different because in this problem setting, we need to consider minimum, maximum error, and so for given test, we need to consider maximum error. But in this case, we have a different problem. So because depending on sigma, we can choose optimum test. Depending on state S, we can choose optimum test. But in this problem, we need to choose common test among that state belong to S. So usually this one is large. Yes, no. Yes, this is large. This is larger, and this is smaller. But we can use convex, convex structure and concave structure. So using this way, so we can apply the minimax theorem. So then, as a result of minimax theorem, we obtain this equality. So then it is enough to consider this quantity. So in our talk, I will only discuss this one. So in this sense, we do not exactly construct the test for this problem. We only discuss this problem. And we often consider a set of permutation invariant states because I previously mentioned that original free set is closed with respect to the permutation. Then we can consider that some subset composed of the permutation invariant states. So we consider this one. And then, for example, this problem equal to this one. So we can restrict the permutation invariant states. And also this minimization problem, yes, maximization problem also restrict to the symmetric states. And also this relative entropy. Also relative entropy minimization of relative entropy also restrict to the symmetric part. So then it is enough to symmetric case. So this is then our problem is slightly easier. So now we want to discuss this problem. So firstly, we choose the minimizing quantity. This one. This is argue minimum. This one. And using this minimizer, so we consider a tensor product of this one. So n is larger than m, and in that case, we can choose some integer n, and that n should be satisfied. This quantity is smaller than m. So this is the remaining part. So you cannot write down this one for any n. So we need to care about some remaining part. So then we this can easily follow this one. So because this one and this is a symmetric case, and this is a larger case. Essentially same. Or I already mentioned that. And once we fix some m, so you can obtain this one. Because this is not optimum. So this is worst case one. So this is the worst one, and we consider some specific one. So this one is always greater than this one. And after taking m infinity, still we have this inequality. And also using the strong converse of Stein's lemma, this quantity is upper bounded by this quantity. So then finally we obtain this one, and this one is equal to this quantity is by definition. So the problem is that this is essentially shown that the converse part is already held. So then we need to prove the opposite inequality. The problem is opposite inequality. So the problem is this one is not so difficult. We show this one by using a contradiction. So firstly, we choose some depending on some epsilon. We consider this quantity. So this one is previously shown that here, or this one. So we choose that this one R1 epsilon. We define R1 epsilon, and we want to show that R1 this one is equal to this one. This is R1 epsilon, and we choose optimum sigma n in this way. So we choose optimum sigma for the in the sense of relative entropy, and we choose R2 in this way, and this one is always greater than this one, because I already mentioned that we have this inequality. So we want to show the opposite inequality. Now we consider that now we consider that if R2 is strictly greater than this one, in that case there exists another sequence of state such that this one is smaller than this one. But this one has some contradiction because this one is strictly smaller than R2. But I already mentioned that we choose the smallest one. So this one should be minimum length about the this relative entropy. But if this is correct, so there exists some state such that the sequence is smaller than this R2. This R2 is smaller than this one. So this is contradiction because we already mentioned that this is minimum state. So then this limit should be minimum. But this one mentioned that there exists smaller than one. If this one is strictly larger than this one. If this one is equal to 0, there is no contradiction because this one is equal to this one. So then we show that R2 equal to R1 epsilon. So this means that we already shown that statement. So the remaining problem, we need to find this one to satisfy this inequality. So this is our requirement. So I mentioned that this is minimum one, but if we show that some sequence such that we satisfy this inequality, so in that case, this is contradiction. So we need to find this state satisfying this one. So then we could obtain the result. This is our story. So now we found that this state. So that's construction very easy. So previously we already discussed this state, and also we consider minimizer in the sense of the this beta epsilon. So the sigma star n. So and also the full rank state. So we need to take this sum. So we need to take some, and also we need to take some pinching. Pinching means that somehow projecting some states projection by application the projection. So then we have another state. This is pinching. So then it is sufficient that we will show that this one because this quantity and this quantity is almost same. The difference of this one is almost asymmetrical, almost zero due to that's pinching property, due to the some property of the how to say representation theory properties. So then we discuss this one instead of this guy, pinching one for with respect to this one. But if the state is everything commutative, so pinching does not change anything. So if everything stays, this one is identity map. So then this one is completely same as this one. If you could not understand that this discussion, you can consider that everything is commutative. So in that case, the story is much easier. So sorry, some Japanese. So then we show that this one. So yes, this is firstly we consider this hypothesis. So original hypothesis testing is low error and this one, but we can consider slightly different guy. So yes, even though we change this one, still we have this one quantity. So this is same. So this is hypothesis testing. Originally, without pinching, we have this equation. But now we apply pinching. So application pinching becomes somehow decrease the performance of hypothesis testing. So then still we have this inequality. But if you consider commutative case, this is same as original one, then this is equal. So still we have this inequality. And the second one is we choose arbitrary epsilon 1. This is much small, almost close to 0. Later we take to go to 0. But in order to apply the strong comma statement, we need some arbitrary small epsilon 1. So using the arbitrary small epsilon 1, we have this inequality. And this is strong compass for the Stein lemma. So this one is somehow smaller than epsilon 0. Epsilon 0 is we choose in this way. So if we choose sufficiently large M, we have this inequality. So because if M is sufficient large, this worst case equal to the R2. So then if we choose additional small number epsilon 0, then there exists M such that this kind of state exists and we have this inequality. So now we need to consider two kinds of projection. So then we have this quantity, but maybe it is better to calculate this one because our problem is calculation of the relative entropy, this guy, relative entropy. So we need to calculate the relative entropy. So what is the relative entropy? Relative entropy is the expectation value of the likelihood ratio, logarithmic likelihood ratio. So this is very important point. So then we need to consider this quantity. So this is observable. This is observable. We need to take log and this rel, and we need to take average of this quantity under this state, So in the classical case, this one can be considered as a kind of random variable. So we need to consider this random variable. So and we consider a cumulative distribution function. But we need to consider this inverse. So if we switch the x-axis and y-axis, this are exactly equal to the distribution function. But we consider its inverse function. So now we have cumulatively increased some function. So in that case, we can easily show that the probability this random variable is smaller than this one is upper bound at least greater than epsilon. So we have this one. This is probability. This axis is probability, and this axis is equal to this random variable. So then we have an inverse of the cumulative distribution function. So the probability is smaller than this bar is equal to the this value. So this one is this probability. This random variable is smaller than this threshold. That probability is this one. This one is greater than epsilon. And also we take the this one. So we take this one. Yes. So the probability this random variable is smaller than this threshold. This one is larger than 1 minus epsilon 1. I will explain this one later. And the maximum of this random variable is lambda. So in this way, so this is probability. So there is some probability distribution, and we need to cumulative something. And we have this value and this value. So then we need to take average of this random variable. So this variable is the upper bound of this one. So then this upper bound is characterized this way. Then we need to take some limit version. So once we take that limitation n equal to infinity, so we can change. We can take limit epsilon 2 and epsilon 1. In particular, epsilon 1 and epsilon 2 can be go to the 0. So then the story much simpler. So upper bound is this one, and we have this one. So the average is around here, and that average equal to this guy, and this is strictly smaller than R. So then we can show that that one relative entropy is relative entropy is upper bounded by this one. So this means that our expected statement. So the limit of this guy is upper bounded by this one. So now I will give you more rigorous statement. So firstly, we give that projection of this one, and we need to make this projection. So we have two projections. So then this means that the logarithmic likelihood ratio is this guy. This logarithmic likelihood is smaller than this one. This is likelihood ratio. This is likelihood between that's log of this one and log of this one. So then we have this probability. So that probability is greater than epsilon, and this probability is 1 minus epsilon 1. So then we need to decompose this one. So first one is this one and this one and this one. So we have some probability and that upper bound is lambda and this upper bound this quantity and this upper bound this. So then we take a limit of this one. So then we have this. So this means that this relative entropy is upper bounded by this way. So in this way we can complete our proof. So this is only 25 minutes. Somehow notation is quite complicated, but calculation is very simple. It is enough to consider logarithmic likelihood function ratio. So then we can calculate this quantity. But of course, somehow this notation is very complicated. But once you're familiar about this notation, you can easily follow this one. At least my proof is much shorter than original incorrect proof. So then this part is finished. So do you have any question? Later I have a next part or resource theory part, but maybe it is better to hear some question or comment about this part. Yeah.
Sorry, what are you pinching with respect to?
Pinching, yes, pinching is this pinching in respect to this guy. Firstly, we make this one, and this one is fortunately permutation invariant. This is permutation invariant, this is Turing, so then permutation invariant, this is permutation invariant. Then we have a permutation invariant state.
Right.
So then we make pinching with respect to this spectral decomposition. Then we can define this one.
Okay. And because it's still permutation invariant. Okay, cool.
Yes.
Thank you.
Any other questions? We can also take questions from Zoom if anybody has.
Maybe in Zoom there are so many experts. But how to speak? They can speak this one. How to communicate?
We should hear it. I think maybe, or they can use the chat.
Where is the speaker? No speaker. But I cannot hear anything. This is mic. There is a speaker.
Yeah, there's a speaker,
something else doing.
but I'm not sure.
I think my course are already joined.
There are no questions in the chat. But maybe the experts have already read the paper and understood the proof.
I hope so, but quite strange. So why people do not comment anything? So. Okay, so okay, now we move to the second part. It is the second law of the quantum resource theory. So now we consider a set of free channels. So this is the input system, this is output system. If the input system dimension 1 has dimension 1, in that case, we have only output system, then this is the set of states. So this statement including the state case. So now we consider that this is free state to states, and we assume that this kind of condition, this is a free channel and another free channel. So then combining these two free channels, so we can make subset of this one. So this one should be included. And also this one should be a closed and permutation, closed set for the permutation. And also, this trivial map. So there is some full state in the output. This one does not depend on the input one. So this kind of trivial channel should be included. So then we consider this quantity. Of course, in the case of states, this one is the same as the previous one, but nowadays we can consider this standard version. But I forget that this J is a Choi matrix for the channel. So in the case of channel, you can prepare maximally entangled state. Then you obtain some final state between the some entanglement half and the output system. So that kind of output state should called choice state, choice state or choice geometric state. So we employ this one. So this one is very important. Using this one, we define this quantity and this one. So essentially, that theory is enough to discuss the choice states. So then we consider the resource theory, but in the case of resource theory, we relax our operation. If we use the usual possible states conversion, as you know, the entanglement distillation and the entanglement cost does not coincide. So the inverse of cost does not coincide the distillation in general. In the pure state case, this is okay, but in the mixed state, this one is not same. So in order to avoid that problem, we relax our set of the free conversions, free operation, super operators. So how can we make this one? So we have this is conversion. So conversion means that there is a channel. This is one channel, and this is another. This set is one set of channel, and this is another set of channel. So then we convert a channel from this one to this one to channel this one to this one. This is the channel conversion. This one sometimes called super operators. In the case of states, there is a free state and there is another free state, and we change the convert some free state to another free state. So this is very conventional one in the case of state case. But nowadays, now we want to consider channel case. So in that case, that kind of conversion is called super operator, because one channel changing the channel is called super operator. Operator means on the some how to say channel, and our conversion change operator to another operator. So then this one called super operators. And in that case, we need to impose some condition for the super operators. So there is a free state, and if the n is a free state, this one should be 0, 1. This is 1. But now, if n is not a free state, so in that free channel, so there is another channel. So then we need to choose some another state such that this convex combination should include in the this free state or free channel. So this kind of minimum is called some robustness. This is very important. So that robustness should go to 0. We need, so this is the condition for our super channel, free super channel. Of course, more rigorous case, usually this one should be 0 without this limitation. Usually, without limitation, this one should be 0. But now we relax some condition. We allow small error. Sometimes that free channel is not after conversion of that free channel is not free channel, slightly different from free channel. But that difference asymptotically go to 0. This is the condition. We want to we make this relaxation. This one is introduced by Fernando's original paper. So we extend that concept to the channel case. So then we consider asymptotic continuity. This one. Yes. So firstly, this Choi matrix with this one means that trace norm. So we consider this trace norm. This trace norm is 0. If these two channels, the trace norm is equal to 0 in the sense of Choi matrix, in that case, after conversion, also this one should be 0. This is a kind of asymptotic continuity. So Of course, if the state case, state conversion can preserve the trace norm distance. So then this condition automatically holds. But now we want to consider channel case. In the case of channel case, we consider this Choi metric. So in that case, after application of the some states, so it is not so easy. In general, this one does not change because application of the conversion Choi met the trace of Choi method does not hold, does not increase, does not decrease. So sometimes increase in general, sometimes increase. We can say monotonicity about the this trace norm of the Choi matrix for the channel conversion. So this is the problem. So then we need to assume this some assumption. Under this condition, we define this asymptotic conversion rate. So there is some free conversion, and we apply conversion, and this one is asymptotic equal to that's Rn copy of the target channel. So then, we want to maximize this that conversion rate R. So this maximum conversion rate R should equal to this ratio. This ratio, this is some previous that asymptotic relative entropy, ratio of asymptotic relative entropy. So this is our result. So how to prove this one? Of course, honestly speaking, for me, this one is more difficult than that open problem. Because this is very complicated theory. Of course, in the case of state, the theory is not so more simple. But in the case of channel, the story is somehow very complicated. We spend more time for this part. So firstly, we need to prove this lemma. This is not so easy, very difficult. So we consider sequence of channel, not free, and this channel is asymptotically the trace norm distance equal to 0 with the n copy of the or some state n. Sorry, this is n1 and this is n1. Sorry, mistake. This one n1 or n1, and under this condition, we minimize this. What is this? Minimize RG. RG is robustness. So we consider robustness and 1 plus this one and take logarithmic. Sometimes this one called logarithmic robustness. So we take 1 over n. So then we can define another this quantity equal to that relative entropy, asymptotic relative entropy. So this is lemma. This lemma is most difficult, very difficult. In order to prove this, essentially we need to employ strong converse part of the Stein's lemma. So then this is quite difficult. But not so difficult. So of course, this is already known because the converse part is not so already known. In direct part more difficult. And then, in order to prove the converse part is this guy. So this conversion rate is cannot exceed this ratio. So in order to prove this, we need to prove this inequality. Proving this inequality is, of course, quite difficult. In this talk, I cannot explain this. But by using that asymptotic continuity for our conversion, we have this inequality. So asymptotic conversion shows that this inequality. Why we have this equation inequality asymptotic continuity. So asymptotic continuity means that asymptotic continuity means that yes, this one and yes, and this one. Yes, asymptotic continuity means that satisfying this quantity, then this quantity should be equal to this one. So then using the right hand this way. So then we have this inequality. So in this proof, in this derivation, we need to use this form. Using this form, we have this inequality by using the asymptotic continuity. So then finally, the definition of the regularized reactive entropy, we have this equation. So then we have this inequality. This is the compact part. And the direct part is more difficult. So in the direct part, we need to employ our new result, generalized Stein's lemma. So we choose that test such that the achieving the performance of the generalized Stein's lemma. So there is this one. So firstly, this error, we need to consider two hypotheses. One hypothesis, this guy. Another hypothesis, set of free channels with this one. So we consider we choose some test such that this error probability goes to 0, and this error is asymptotically go to exponential this way, asymptotically this way. So this is exponential rate. So this kind of two condition is satisfied due to this generalized Stein's lemma. So then we choose some state N2 Rn satisfying this one. This one, why they are exist? This one comes from the previous lemma. So we need to remember this one. So there exists some state, some channel N children N such that satisfying this condition. So then we have that channel in this way, and also there is another channel N2 prime. So this one is satisfying this one. This is definition of the robustness. This is definition of the robustness. There exists some channel satisfying this. This is definition of this robustness. So then we define conversion. There is an input channel. So then we convert to this way. So this is very, very artificial. And this one cannot be realized in the real operations. But using the trick of the resource theory, this one satisfies required condition. So then we can achieve that resource theory result. So of course, this one is mainly follow the original Fernando idea, but his case only discuss the state case. We extend to the channel case. So then we have proved the generalized Stein's lemma, quantum generalized, and using this, we have derived the second law of quantum resource theory, even for the channel convergence. So the above case contains the case with the state resource theory. So thank you very much.